Okay, we shall begin. So now we are entering kind of finding patterns and trends in your data and whatnot. You guys, I think everybody's settled down on a data file and a project and things like that to be working on, and some of you might want to change things, and some of you might want to meet with me again. So please just contact me and say, hey, I want to meet. I want to kind of run these things by you. And anyway, I thought today we could just talk about, as in the remaining weeks, we'll talk about how to kind of model your data. Okay, and what we mean by that, so your report, there's going to be a large part of it is going to be kind of exploratory. A lot of it you'll just use kind of the tidyverse tools, ggplot and dplyr, to kind of find patterns, trends, and summaries, and you'll share those and comment on them, and then you can do further analyses. And so what we'll cover today can fit in both exploratory and modeling, okay? And what we're going to look at specifically is linear regression, okay? Now you will take a full course, well, a lot of you will take a full course on linear regression, and that is Stats 101A, okay? Stats 101A. And linear regression is kind of this, it's been around for a while. It's, we've solved it. It's been studied. It's still probably one of the most useful tools in your toolbox, right? You have a lot of newer models and newer techniques just sound cooler, right? You say, oh, I'm going to fit a neural network to my data. I'm going to fit this random forest or this hierarchical clustering model, or all of these things. They sound so cool, and honestly, your performance gains for some of these things might be like an increase of 2% in performance or something, versus just a classic linear regression model. And with a linear regression model, you have great interpretability. You can look at it and you can understand what is being said. Whereas when you fit a neural network, sure, maybe your predictions come out a little bit better, maybe, okay, and that's not even a guaranteed thing. But then if you ask, well, how does it work? Your answer is going to be, I don't know. Your answer is going to just be, well, I put in the data and we trained it, and now this is what it predicts. Why? I don't know. Okay, it's neural networks. It's very hard to understand what's happening. Linear regression is easy. Okay, in linear regression, so let me just kind of show you with simple linear regression, you're basically going to find a slope and an intercept, and so if you want to follow along, you can follow along. If you just want to watch, just watch. Okay, I'm going to just load up a few of the libraries. The MDSR and Mosaic kind of, I think the data comes in Mosaic, and yeah, so we're going to take a look at that. The data we're going to look at, and I'm following, this is from our textbook. In Appendix E. Okay, Appendix E. It's not like a regular chapter. All right, so the first thing we can do is we can do glimpse rail trail, or in the environment we can just also do capital V view rail trail. Okay, and so this is the data that we have. All right, we got the high temperature, the low temperature, the average temperature, and we could ask, what is this, right? So a lot of times, if you have a data set in R, it will come with at least a description. This will try to provide a lot of the background information that you need to have, right? So when you're thinking about your data set and how you're going to describe it, take a look at kind of the help pages, and I would say you probably want at the very least, as much information as contained in a help page. Probably you'll need to probably need to expand kind of the description, expand the details. But at least at the very minimum, take a look at how the format for the variables and what their descriptions are and things like that, and things. Okay, so here we're looking at the kind of they said they set up a laser beam, okay, between April and November. They looked at 90 days in Florence, Massachusetts, okay, and they were just kind of like walking, when somebody walked past, it's kind of like you go into the convenience store at the gas station and you walk through that little light sensor and it goes ding dong, right? Basically, they set something up like that to see to estimate how many people were walking on the trail, okay? And so anyway, and then they measured a bunch of other stuff, right? The high temperature, low temperature, average temperature. Was it in spring, summer, or fall? Cloud cover, precipitation volume, weekday, and day type, okay? And so notice how, and this you might have to do, depending on your data set, you might have to do some variable conversion into what we call indicator or dummy variables. So you could imagine the data was recorded where the column was just season, and the person wrote spring, summer, fall in the season, but when it comes to analysis, it's hard to use that kind of categorical variable. And so what did they do? They converted the season, which had 3 different things. I guess nobody goes in the winter. And they turned it into 3 columns. And spring is 0 or 1, summer is 0 or 1, and fall would be 0 or 1, okay? And so basically, and so this fall column is completely redundant. It's technically unnecessary because if it's not spring and if it's not summer, then it has to be fall. So technically, the inclusion of this variable fall is completely redundant, but it's also fine if you wanted to do a quick analysis on like whether the thing was in fall or not. Okay. But anyway, what we're going to try to do is we want to just say, hey, what's the relationship between this and say the volume, right? The estimated number of trail users that day. And so, if they walked through the sensor and they broke that laser line, then it registered as a person going on the trail. Now it's possible somebody saw the laser line and like a kid, they were like kind of hopping back and forth and trying to set off the thing. I don't know if you ever did that as a kid or maybe even as an adult, just to kind of set off the, have these things register. So anyway, what we will do is we'll just kind of explore things, okay? So, one thing we can just start off with is with a simple plot, all right? And so we'll do a ggplot, and let's just take a look. So we'll do a rail trailer. Perhaps I will do rail trail, and we'll pipe it into ggplot. And let's just explore the relationship between the temperature and the volume, okay? And so we'll do plus, and we'll do geom underscore point. All right, and then we'll just create a plot there. All right, so this is what it looks like. And we go, okay, well, is there anything there? And one thing we can do is we could just kind of see if there's like a straight line. So it does seem, our intuition would tell us, all right, when am I going to go hiking, okay? I don't want to go hiking when it's super cold, and I don't want to go hiking when it's super hot, but in general, when it's warmer, I'm more likely to go hiking. And it looks like in Massachusetts, you don't really run into the problem of it getting like 100 degrees. I mean, it looks like there were a few days where it was like over 90 and stuff, but it's not like, well, I don't know. We have one person from Boston here, but it's not like when some days during the summer, or even in September, it'll be like 102 or something, and it's just like, it's dangerous to go hiking on a day like that. So, so what we can do is we could fit a straight line, right? So one of those things would be geom smooth, and in here we will just say straight line will be method lm, okay? And so it fits that, okay? So this is kind of the straight line that it fits. All right, so how do we actually figure out what is the slope and intercept of this line, okay? So this is done by using a package called, or not package, a function in R called lm. lm will fit linear models. So you do lm, and in our case, we're going to do volume as described by the high temperature, okay? And we say data is coming from rail trail, right? And this creates a model, okay? Now, what we want to do is we want to store this model, okay? And so I'm going to create an object called mod, or we can call it model or something, right? And basically, when you say lm volume as described by high temp, we're saying I want you to predict the volume using that day's high temperature, okay? And right now it's a linear model, okay? Which is very kind of limiting. It's still useful, but it's limiting. It just says, hey, if the temperature goes from 40 to 50 degrees, okay, if the temperature goes up 10 degrees, we're expecting the number of people walking on the trail, I don't know, maybe it goes up 70, okay? Every additional 10 degrees, maybe it goes up 70 or something like that, okay? And, or let's 60, I don't know, okay. And basically, a linear model says the jump from 40 to 50 is going to be the same as the jump going from 70 to 80, the same as the jump going from 80 to 90, the same as the jump going from 90 to 100, the same as the jump going from 100 to 110, so on and so forth, okay? Now, few things in life are perfectly linear like that, and it continues on forever. So a lot of times it'll be linear for a certain portion of the data, but then to assume that this trend continues forever in either direction probably is wrong, okay? But at least maybe for our data, we'll say, yeah, this is what happens, okay? So the command to create it looks like this, okay? And again, because there's an assignment thing, it looks like nothing happened, okay? And so we can ask, okay, well, what are the details of the model? We can ask model, we can ask summary of the model that we created, all right? And it outputs some stuff down here. And it says, okay, these are your estimates. Your intercept, -17, and the slope is 5.7. Okay, the intercept being negative just doesn't work, okay? What we're trying to say is we're basically saying the predicted volume is equal to -17 plus 5.7 times the temperature, okay, or the high temperature of that day. So if the high temperature was 100 degrees, we would do 5.7 times 100 degrees, 570 minus 17, and we would say, I predict a volume of 453, okay? If the high temperature was 50 degrees, 5.7 times 50 is 285, I don't know, 285 minus 17 is 258, okay? And we're getting some kind of number like that, okay? So, something like that, okay? That's pretty much what we're saying. Now, to kind of get it a little bit, so the output and summary looks like this, which is nice. Okay. Sometimes you want to work with those things, and there's a package called Broom. All right. And it's it's just a kind of a play on words. It's kind of the idea that we're going to tidy up the results of our model. Okay. So there's a function called tidy. Tidy basically the results of the model. And what do you see? After running tidy the model, okay, these numbers down here, tidy model, are basically the exact same numbers that appear here, okay, except now they are formatted to be in a tibble. And so if I wanted to reference these things from a tibble, I can, right? Whereas over here, if I wanted to kind of get these values, it's a little bit trickier, okay? But now I can actually reference them from being inside of a tibble. Okay. So what exactly does this model do? Okay. Is we are trying to, we want to know, hey, does it actually improve? Does using temperature actually improve our predictions? Okay. And so we're getting, when you look at this, p-value, okay, what does it mean to have this p-value that's 1.7 times 10 to the negative 9? What does this mean? The p-value for high temp is 1.7 e to the negative 9, okay? So very small value. Yeah, what does it mean?
Whatever your null hypothesis is, you probably reject it.
Okay, reject it. All right, what is my null hypothesis? All right, so small p-value means we reject our null hypothesis. Okay, what was the null hypothesis? Basically, the null hypothesis is, well, at the very simplest, is the slope for high temperature 0 or is it something else? Okay, so the null hypothesis is slope for high temperature is 0, and the alternative is that the slope for high temperature is not 0. Okay, and basically we are saying we have data. The data provides evidence that the slope associated with high temperature, okay, so our conclusion, the slope associated with high temp is not 0, okay? And our data provides evidence that it is positive. I mean, just looking at it, we can see that. All right, maybe more specifically, this number is based on a reduction in the sum of squares. A reduction in the sum of squares. Hang on, before I get ahead of myself, let me give you your first view quiz answer. Today's first view quiz answer is D. D, as in dog. Okay, so week 7. What are we doing? This is just linear regression demo. Okay, so our data provides evidence that the slope is positive. I'm gonna, let me just go to the MDSR textbook, and I'll just show you the diagram that they have here. Rather than taking the time to reproduce. Okay, so this is what we have. Okay, so here, okay, simple linear regression, we are saying our values y are equal to an intercept, which we call beta 0, plus a slope times whatever x is, okay? And then there's some error term indicating that we're not going to be able to capture all of the information there. There's always going to be some variation away from the line. That's fine, okay? And we have this diagram, okay? Which might feel like totally, what is all of this? Okay, what's going on here? What we are saying is that this is the null model. The null model says, taking into account the temperature of the day isn't going to help us make predictions about volume, okay? So under the null hypothesis, we're saying the slope for the high temperature is 0. Taking into account the high temperature isn't going to help me make better predictions, okay? And just some days, there's a lot of people going on the trail. Some days, there's fewer people going on the trail. Taking into account higher temperature isn't going to help us make better predictions. And so really, just ignore the high temperature. The best value you should predict is just predict the average. Just predict the average. That's what the null hypothesis says. The slope is 0, okay? Just predict the average. And so we have a line right here where the slope is 0. It's a flat line. And we're just saying, just predict the average for everybody, okay? And in some cases, like for some models like that, that might be the truth. That just predict the average. Don't try to figure it out, right? So it'd be kind of just like, you know, is knowing the temperature going to help you figure out if, you know, how many points were scored in the basketball game? Probably not, right? Basketball games are played indoors, and probably the outside temperature probably not going to make a huge difference, right? So if we're trying to predict how many points were scored in the basketball game, knowing the high temperature probably not going to help us. It's probably just better to just predict average for everybody, okay? So anyway, according to the null model, we could say, well, how big are our residuals, okay? So we look at every single point, and we say, well, how much error do we have? So here's what we predicted is the average, and the actual value is down here. We predicted the average, the actual value is down here. We predicted the average, the actual value is down here. We're going to take all of these residuals, we square them, okay? This is the idea of the squared residuals, the sum of the squared residuals. We take all of these straight lines, we square them, and we say, okay, what is the total sum of the squared residuals? What is the total sum of the squared residuals? Okay. All right. Over here, we say, well, I think the slope should not be 0. That high temperature, when the high temperature is low, we should predict lower values. When the high temperature is high, we should predict higher values. Okay. And so when we do that, we say, okay, well, how much are our residuals? And we say, okay, well, for this dot, the residual is a lot smaller because we're predicting down here, and the actual value is down here, right? Over here, the residual is like this, okay? Now, some of these, we still have really big residuals, okay? We predicted here, and the actual volume was like way up here, okay? And over here, we're actually getting worse performance, right? For this point, with a very high temperature that day, the volume wasn't very high, and what we predicted, it wasn't very different from the average, okay? Whereas over here, according to our model, we're saying, it's really hot, the high temperature is high, therefore we're going to predict a lot of people going on the trail, and that was a bit mistake. Okay, so we now have a very big residual. But if you take all of these residuals and you square them up, the total sum of squares residuals here is a lot less than the total sum of squares residuals here, okay? And we're saying this kind of difference where we were able to reduce the amount of sum of squared residuals over here is, that can't just be a result of just kind of randomness, okay? Because we can't just explain this away and just say, oh, you know, we just got just some weird sample where this happened to be the case, okay? There's an indication here that, yeah, the slope is not 0. Actually, using the slope is going to help us reduce the predicted, the residuals there, okay? All right, is that okay? Yes, question?
Well, how do we interpret the p-value for the intercept?
How do we, yeah, so over here, the p-value for the intercept is 0.774, okay? And what we're saying is that, you know, the value that's going to minimize my squared residuals is, right now, based on the data I have, is -17, okay? And we're asking, well, is that significantly different from 0? Is that significantly different from 0? And according to our calculations, the p-value being a very big number indicates that we don't have strong evidence that it's different from 0. It could be 0, okay? We're not saying that it is, but it could be 0, okay? So if we want to say that the, you know, when it's 0 degrees outside, you know, we would expect the volume to be 0. Like that's a reasonable thing. But then again, you know, the temperature can also go negative, and so then you'd still get in it, you know. So all we're saying is that right now this intercept is estimated to be -17. Is that -17 significantly different from 0? Right now the answer is no. Okay, that's what the thing translates to. Okay. There are, when you look at kind of when you look at the summary, you get a r² value of 0.339. There's an adjusted r² of 0.332. I don't want to get super into this, okay? But this is kind of how much of the variation is explained, and it's basically the amount of reduction in the sum of squares, okay? So when you look at this plot, and if you take all of the residuals and you square them, you'd get a number. You get a big number, okay? When you take all of these lines and you square them, and you add them all up, you get another number, okay? The sum of squares for this is smaller than the sum of squares for this. How much smaller? The reduction is around 34% smaller, okay? So I don't know what the original sum of squares was. Let's say it was a 10,000, okay? So if you take all of these lines and you square them, let's say we get 10,000. Over here, what we're saying, because we got a 0.34, if you take all of these lines and you square them, you'd get something around 6,600, okay? A reduction of around 34%. Okay, that's what this multiple r² value is, okay? A bigger number generally means something more successful. Now, you don't want to be guided only by r², okay? Because what I'll do is we can add variables, and every time we add a variable, we're going to be able to squeeze out a little bit more explanation power, okay? All right, so here we could say, we can make our model a little bit, we're going to add a variable to our model. Okay, so now we're going to have, we'll take two variables into account. The temperature and whether it was a weekday. Okay, weekday, if you take a look, weekday is a categorical variable, okay? True or false? Okay. Is it a weekday? Yes or no? No. Okay. And kind of we would assume that on days where it wasn't a weekday, there might be a little bit more volume on the trail, right? Because generally slightly more leisure time. So let's see if this even makes sense. First we'll so what we can do is we can fit the model, okay? And so how do we do this? We're going to create a second model. We'll call this the parallel model. And the way we write the model is we say, okay, the value that we want to predict is volume. So that goes in front of the tilde, the squiggle, okay? And then we say, okay, what variables are we using? The temperature plus the variable weekday, okay? The data still comes from rail trail, right? So we do that, we create this thing. We can say, all right, show me the summary of this model. Okay, and so we get this. And it says, okay, so we still have a slope here. And then if the weekday is true, that reduces our volume by around 51 people. That's our guess. Okay? And if it's not true, then we don't reduce the volume. That's kind of our number. So notice our intercept here is higher now. Okay? Our intercept is now 42, and we would add 5.3 times our temperature, and then if it is a weekday, we'll subtract 51. That's kind of our number. Did you have a question?
Yeah. So, So my question was, when you do high time plus weekday, you're not like physically adding them together. You're just passing two arguments, right?
You're passing, yeah, you're passing two variables in there. You are also physically adding them. The model, I need a, so I don't actually want this. Okay, so we're just saying this is our intercept plus beta 1 times, I'm going to just call it temp. It's high temperature, all right, plus beta 2 times weekday, all right?
Oh, sure. Yeah, so you're adding like some scale version.
Yeah, you have some, you're taking weekday. Weekday is either a 0 or a 1. 0 when it's the weekend, 1 it's when the weekday, and you're going to multiply it by some constant, okay? And right now this constant's estimated to be something around 50, 51. So you take the intercept, you take the slope, you multiply by your temperature. So if the temperature was 50 degrees, you do 50 times, 5.5 or so, whatever. You say, all right, let's add 280 something, okay, to our thing, and then it's not a weekday, we can leave it, right? We don't, this zeroes out, weekdays at 0, we don't have to worry about this. Okay, if it is a weekday, this number we're going to subtract, we're going to do weekday is 1, B2 is negative 51. We're going to take whatever my estimate is for the weekend, and I'm going to just subtract 51. Okay? So that's what we have here. We can also throw it into the thing to kind of get the same values as a table. All right? This p-value it's not incredibly tiny, but it's certainly it's less than 5%. So we might say, okay, we seem to have data here. All right, let's okay. Now there's a few things we can do, right? So there's a function called augment. Oops. I call this model parallel, right? And it takes basically all of the rows, okay, in rail trail. Okay, so here the original data, there's 90 entries, okay, and we have the volume is 501, the weekday is true, and we're using the high temperature, okay? And so when you take the model and you throw it into the argument augment, it takes those variables that we're using, volume, high temperature, weekday, okay? And then it takes the variables that you're using, and then it says, according to our model, what do we predict? The fitted value is 435, okay? What's the residual? It gives you a whole bunch of stuff, okay? So it basically says, for all 90 values in your original data set, someone's computer's about to take off like a jet engine here. We're gonna, it's taking the variables that we're using, and it's giving you basically the values, its predicted value, and things like that, okay? And so what we can do is we could take this table and then create a plot based off of that, okay? So what does this look like? So Augment shows all of the original values plus the predicted values and residuals and other stuff. Okay, so what we're going to do is we're going to do augment model parallel. Okay, and then I'm going to put this, let's make a plot out of it, ggplot, right? What do I want to do? We still want to have high temperature on the x variable. Let's put the volume on the y variable. Okay, and then let's color the points based on whether it was a weekday or not. Okay, so we're going to have some points for the weekend, some points for the weekdays. Okay, let's plot this. Okay, all right, and so here we have just weekdays and weekends. Okay, and so you know the really high numbers, we can see, oh, those were all weekends. Okay, those were all weekends. Yeah, question.
So it says augment would give the predicted value. So
yeah, it would also give us the predicted value. Now technically, as far as this goes, I didn't actually have to augment this. Okay, right now I didn't have to augment this, but what we're gonna do is I'm gonna add a line. Okay, and we're gonna do geom line, and for this thing, for the line, we're going to change it. So whenever you add something and you don't provide any AES arguments, it's going to inherit the arguments from ggplot. Okay, so in ggplot we have x is temperature, y is volume, color is weekday. Okay, when I add a line, I don't want, like here, if I do this, it's going to try to connect. It's going to try to connect all the blue dots together with a line, and it's going to try to connect all the red dots together with a line. Okay, we don't want to do that. Okay, so what we're going to do is we're going to say just change the mapping for the line only. For the line, don't use the actual volume numbers. Use the fitted numbers. Okay, does that make sense? Use the fitted numbers rather than the actual numbers. So right now the lines are using the same as the actual numbers, and so it's connecting all the dots which represent the actual numbers. We don't want that. We're going to say, draw me a line, okay, but use the fitted numbers, okay? And so the fitted numbers look like this and this, okay? And so here we have two parallel lines, okay? And basically one is going to be where did my values go? One is 51, or basically 51.6 lower than the other one. And so if it's the weekend, we predict values along here, and if it's a weekday, we predict values along here. Now, is this the best model? Probably not. Okay, probably not. But at least it's giving us some indication, right? Things that we can take into account when we're studying and trying to explore relationships, right? And this aligns with our intuition, right? We say, okay, well, yeah, people are more likely, right? And what we might need to do is we might probably, to make our model stronger, okay, we might need to allow for non-straight line relationships, right? We could have kind of non-parametric relationships or things like that, okay? Do these, I want to make sure we're kind of comfortable with how we are creating these plots, okay? Because as you guys start exploring your data, really, there's so much you can do just with ggplot, dplyr, and the tidyverse as far as exploring these things, okay? And if you're if you have an idea and you say, I want to figure out how to kind of slice something a certain way and kind of plot this or things like that, and you're just having trouble figuring out exactly what needs to be done, don't hesitate to come to office hours and ask me for help. I'm not going to promise that I can figure out every single one of your answers, but I feel I feel like I might be able to help you guys, okay? And so so don't hesitate to ask, all right? So this is one where we're just saying the effect of a weekday is a constant, okay? Down here, the effect of the weekday, whether weekday or weekend, the difference is 50. Over here, the effect of the weekend versus weekday is still 50, okay? We're saying it's a constant effect. So these two lines are parallel. Now, you can also take into account, perhaps, depending on the temperature, whether it's a weekday or not, the effect changes, okay? We call that an interaction between the temperature and the weekday variable, okay? So I'm going to call this model interact, all right? And there's more details in the textbook in this appendix that if you're going to use linear regression, it's something you should take into account. Oh, I forgot. Second view quiz, I'll just give you your last two view quiz answers. E as in elephant is your second one, and A as in apple is your third one, okay? E as in elephant is number 2, A as in apple is number 3. Okay, and so how do we take into account that the weekday and the high temperature of the day have an interaction? It seems a little bit funny, but you just multiply the two things together. All right, so the command is volume is predicted by taking to the temperature, add the effect of the weekday, and multiply the temperature times the weekday. Multiply the temperature times the weekday, and we'll get a result there, okay? And let's just go ahead and let's just take this exact same thing here. All right, except instead of model parallel, we'll do the model interact. Okay, and let's just kind of plot this. All right, and so now we have different slopes for these two lines. What does this mean here? It says, you know what, when the temperature is low, whether it's a weekday or weekend, that has a big effect, okay? And when the temperature is high, whether it's a weekday or weekend, has a smaller effect, okay? What exactly does that mean? Okay, maybe we should look at the kind of the summary. Is this Okay, and here what it says is, okay, you know, when you take into account the interaction effect is might not be significant. Okay, we get a p-value of 0.29, and in fact, including both of these things, both just whether it's a weekday or not, and the interaction, you know, both of these things end up being not significant. But at the premise, it basically says, you know, kind of when the temperature is high, I guess you're going to get similar amounts of people going out for a hike. Okay, whether it's a weekday or a weekend, you're going to get similar amounts of people going out for a hike. But for whatever reason, when the temperature is a little bit lower, on the weekday, people aren't going to go out for a hike, but on the weekend, they're more likely to go out for a hike or something, okay? But again, you look at the data itself, you look at these dots, and you say, wow, I don't know if this line is doing that great of a job fitting these dots either, right? So there's a little bit of, there's always, you know, you have the tools, but also look at it with your eyes and just say, hey, is this thing that I'm kind of predicting, is this line that I'm fitting, does that even make sense? These are kind of good places to start and just kind of ask questions in the beginning, okay? Yeah, question. What's that?
I have a question about the high temp times weekday.
High temp times weekday, yeah, what's your question?
So when you add all these things, they're all just like cold methods that are like changes predictors as well, right?
Yeah, so you have high temp,
That's yellow high temp.
that's a column, weekday is a column.
Like high temp on weekday, like some zeros and some high temps.
Yes.
Okay, and just treating that as a potential predictor of volume.
Yes.
Okay.
Yes.
It wasn't like some weird syntax.
Yeah, it's okay, I guess you don't have the they don't create a third column, but yeah, basically for some of the values you're going to have 83, 73, 74, and then you're going to have a 0, something like that. Yeah. So it's pretty much like that. Okay. Okay. This is just very, 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 very brief introduction, and you know, we really only have a couple weeks left. Okay, we've got Friday of this week, and then we pretty much have 2 weeks: week 8, week 9, and then during weeks 10 and 11, you guys will be doing final group project presentations and stuff. So I'll give you more and more details, but please do you should be working on this in groups for at least a few hours, both individually and together, collectively, okay, just to kind of explore the data, ask questions, see if you find things. And don't feel like every question you ask has to have an answer of there's definitely effect. You can say, we explored this thing, we were curious if there was an effect, and after exploration, we came to the conclusion that there's not much of an effect. That's a perfectly fine thing to state. Okay, don't feel like everything has to be like, we explored this effect and we found this, okay? Really, I want you guys to just get comfortable with the idea of exploring the data, slicing it in different ways, and checking out for different kinds of potential effects, okay? That's what a lot of this beginning stuff is all about. Okay, thank you guys. We'll see you guys on Friday.